the last talk is given by Partha Niyogi, and it is a geometric perspective on machine learning.
Thank you. I'm going to tell you a little bit about an approach to pattern recognition, machine learning, and related problems that we have been pursuing for some time now at Chicago. And this is an approach in which the geometry of the underlying probability distribution that generates the data will play a very central role in developing representations, in defining suitable classes of functions with which we will operate, and ultimately in designing algorithms for a variety of tasks from pattern recognition to numerical analysis. Now, the context in which all of this arose is actually the context of high dimensional data analysis, which is the theme of this workshop. And increasingly we live in a world where we are confronted with large amounts of very high dimensional data, and a natural question to ask is, under what conditions is it possible to do effective inference without running into this so-called curse of dimensionality? I should emphasize actually there are two different curses of dimensionality. There's the informational curse of dimensionality, and then there's the computational curse of dimensionality, which computer scientists typically study through complexity theory. I'll give you an example of that later in this talk. But one can approach this general question from many different points of view, and there are at least three that I've identified. One, which is perhaps the most classical, is the point of view of smoothness. So, for example, if the regression function that you're trying to learn is very smooth, belongs to a Sobolev space of order S, and S itself is order D, where D is the dimension, then of course there is no curse of dimensionality. So, if you're trying to learn a regression function which is smoother and smoother in higher and higher dimensional spaces, there's no curse of dimensionality, and that observation leads to a class of algorithms that try to maximize smoothness. The other point of view, which is more recent and has been discussed quite heavily here, is the point of view of sparsity. So, if the regression function is not smooth in any natural sense, but is sparse in some basis, then good things can happen. And there is a third point of view, which maybe doesn't reside at the center of statistics, but somehow is at the borders of statistics and computer science and mathematics, and that's the point of view of geometry, and that's what I want to tell you about. And Ann Lee actually gave you a sense already, the geometric point of view is this, that natural data, although it lives in a high dimensional space, cannot possibly fill up the whole high dimensional space uniformly. That's absurd. Okay? So, it must concentrate around some low dimensional structures or some geometric structures which are far from uniform. Now, if this natural data is actually generated by a system with few degrees of freedom, then under some conditions this geometric structure will actually have the structure of a Riemannian submanifold. But more generally, it has some geometric structure which we can then exploit, and if the manifold is actually low dimensional, then all rates are governed by the dimension of the manifold, and you will in some sense reap the blessings of this low dimensional manifold without necessarily realizing it sometimes. So, this geometric point of view has given rise to a field which has come to be called manifold learning, and if you take this point of view, you can ask what sorts of algorithms are inspired by this point of view, and what sort of theoretical questions come up in the analysis of these algorithms. And that's what I'll tell you about over the next hour or so, and hopefully what you'll see is how ideas from geometry and topology, ideas from probability and statistics, and ideas from computer science, graph theory will come together in a very natural way in this enterprise. So, manifold learning. Manifold learning is not really a single problem. A lot of people think it's actually nonlinear dimensionality reduction. So, I just want to emphasize that it is not. Manifold learning is really a collection of problems unified by a common assumption, and that common assumption is that the data lives on some submanifold M of Rn. Okay? Now, in this common setting, you can look at all the classical questions of statistics and learning. You can look at clustering, classification, dimensionality reduction, and so on, and many of these questions reduce to learning essentially a function from M to some space, typically the reals in regression, or maybe a finite set for classification or clustering. Now, if the manifold M was known to you, then this would be just a technical exercise. You would have to do exactly what we normally do and then just do it correctly on a manifold. What is interesting in this setting actually is the manifold M is actually not known to you. So, you are in this very curious situation where you are trying to learn a function and you have to learn both the function and its domain simultaneously, okay? And that can make a very big difference in practice. So, therefore, if the manifold M is unknown to you, it gives rise to a very beautiful problem, okay? If there is a submanifold of Rn and I sample this manifold and give you a bunch of points, so you have this cloud of points sitting in a high dimensional space, but residing on some manifold in this submanifold in the space, what geometric or topological properties of this manifold can you learn, so to speak, or infer from data? Okay, so, this is a question you can study in some abstraction, and we will look at some of these kinds of questions. So, the take home message of what I want to sort of communicate to you is really this is it gives rise to a whole geometrically motivated approach to learning, in which one might think of it as a kind of a nonlinear, non-parametric approach, and the starring role of the story, the hero, is really the Laplace-Beltrami operator and the associated heat kernel, which are sort of two sides of the same coin. And you will see again and again and again the Laplacian and the heat kernel appearing in a number of different settings. So, at least three settings I will show you, and they are quite different. Before I do anything else, I just want to give you one example. It is an example which is very close to my heart, because I spent quite a lot of time working on acoustics and speech, and this is an acoustic example to show you how data could actually lie on a low dimensional manifold. So, here is the example. Okay. Imagine a tube of length L. Okay. It is a single tube of length L, and imagine that I blow puffs of air from one end of the tube, u of t. So, I am exciting this tube by puffs of air, and what I get at the other end of the tube is the sound that comes out of the other end of the tube, s of t. Okay. So, every day you come to me and you measure the sound that I make that day. What I am doing from day to day is I am keeping the excitation fixed, u of t, but I am just changing the length of the tube, L. Okay. So, here is a textbook example, and you can work this out. You solve the one dimensional airflow in this tube, assuming planar wave propagation. You look at the volume, velocity, the pressure, and so P of x comma t is the pressure wave as a function of time at location x, and the measurement s of t that you are making is actually just P of L comma t. Okay? That is what you measure every day. There is only one degree of freedom that is generating the data for you. Now, if u of t is actually a periodic excitation like puffs of air or like your vocal cords vibrating when you are producing a sonorant sound, then u of t lives in little L2. Okay, it has a Fourier series expansion. S of t also lives in little L2 because of the linear transformation. Okay, so, every day you come, you measure a point in little L2, you take all the different Fourier coefficients of this point, you go to your infinite dimensional computer and you plot this infinite dimensional point. Now, what is interesting, because this is actually just an example you can work out, is that naturally you see right away that all these points from day to day lie on a one dimensional curve embedded in little L2, and this curve is actually very complex. That is what is interesting. So, if u of t looks like this, s of t will look like this, and of course, I have just plotted beta 1, beta 3, beta 7, just projected this into 3 dimensions. The interesting thing about this curve is it does not lie in any finite dimensional subspace of little L2. So, it just curves all around like this messy thing, but it is a one dimensional object. Actually, there's a long tradition in acoustics of modeling the vocal tract as an irregularly shaped tube excited by puffs of air at the glottis. Okay? And assuming you don't have so many degrees of freedom in your vocal tract, the same argument will tell you the set of all speech sounds would lie on some possibly k-dimensional manifold in L2. So, I want to just give you an example. If this works, because the thing didn't quite work.
Bat, butt, beat, boot.
So, let me play it again. This is probably the most interesting
Bat, butt, beat, boot.
So, hopefully you heard bat, bot, beat, boot. Okay. Bot is actually bought with an American accent. So, it's bot, bat, bot, beat, boot. These sounds were generated by two tubes put together, L1, L2, excited by a periodic excitation. And you see, with just two tubes put together, you're already getting the perceptual effect of real speech. The rest are sort of details of all the higher harmonics somehow. Okay. So, in some cases, and some people have talked about this, in many examples, you can give a formal argument, just like I did, of why data would actually live on a manifold. Okay. In some other cases, like Anne talked about, you may actually give some empirical argument which you discover through looking at the data, like the data set on 3 by 3 patches, where data might live on a manifold. And I am going to sort of argue that manifold plus noise is a very generic model for modeling high dimensional distributions. And the simplest kind of manifold plus noise model, the very simplest kind, is actually one which is very familiar to statisticians, the mixture of Gaussians. So, the mixture of Gaussians is a manifold which is just k points, the centers of the Gaussians, plus noise in the normal direction. Okay. So, now with this point of view, let us look at some problems. Okay. So, this is just a point of view, and now we will have to see if this point of view allows us to do something useful. So, we are going to start with pattern recognition, and just to make sure we are on the same page, here is how the problem is set up. There is a probability distribution P on x cross y, okay, such that labeled examples xi, yi pairs are presented to you, and your goal as a learner is to find a function f from x to y, which generalizes well. Now, of course, you see right away this is ill-posed, because there are infinitely many functions that would interpolate the finite amount of data that you have. So, any reasonable process will actually have to have some notion of simplicity to find, in some sense, the simplest function that fits your data. Okay? Model selection in some way. So, here is an example. I give you two class pattern classification. I give you two examples, one red, one blue. That is labeled plus, this is labeled minus, and I ask you, give me a classifier. Now, this is actually the hard reality of those who work in the trenches. They have a finite amount of data and they have to do something. Okay? Now, what would you do? There are infinitely many functions that fit this data, but somehow it seems that the most reasonable thing to do is this. Now, you can ask, why is this a reasonable thing to do? And in some sense, learning theory and statistical theory and all of that is just constructing elaborate justifications for why this is a reasonable thing. Okay? So, you could say this is the maximum margin classifier, this is the smoothest spline of degree 0, or this is the minimum description length classifier in some coding language, or whatever. Okay? Choose your religion, but you have to have a notion of simplicity. Now, I will express this notion of simplicity in the regularization framework. So, what I will say is I am going to choose a kernel K, which will define for me a reproducing kernel Hilbert space H of K, and then I will basically do penalized least squares in this reproducing kernel Hilbert space. So, this is ridge regression. Okay. Now, notice that if you change that least squares loss function to a hinge loss, you get exactly support vector machines, exactly, not approximately. Okay. And of course, if you change it to a logistic loss, you get logistic regression. And if you interpret the kernel K as a smoothness function in some ways, then you essentially get splines. So, this is fairly general, and many algorithms are accommodated in this framework. So, all of this is of course known and understood, and now here is my point where geometry comes in. I am going to say that simplicity is relative. So, now I am going to give you one red example positive, one blue example negative, and infinite amounts of unlabeled data. I am going to reveal to you the structure of the marginal distribution P of x, okay? And this is the picture. Now, I am going to ask you, what classifier would you like to build? You still have the same number of labeled examples, one red, one blue. Now, unless you want to be perverse, I am going to say it is self-evident somehow that this is the classifier you are going to build. So, whatever logic or whatever simplicity principle led you to construct a linear classifier in case 1, that same principle should lead you to construct this classifier. Okay? And so, now we want an algorithmic framework in which this turns out to be the case. Now, why did we actually think this is a reasonable thing to do? Well, we saw a few things, right? We saw that the support of the marginal has a manifold structure. We saw immediately that there were at least two notions of distance, a geodesic distance and a Euclidean distance, and possibly more. We have learned about the diffusion distance. We see that the geometric structure of the marginal can affect our notion of what a good simplicity functional can be. We see that there is a difference between the function defined everywhere in R2 and the function restricted only to the manifold M. And so, functions could be smooth along M and rough in the normal fibers, right. So, all of these intuitions somehow we would like to accommodate. Now, I want to give you another example for a reason. There is something a little misleading in that picture that I showed you. There are two circles, and of course, that is a manifold with two connected components, and you could pick up on the manifold part of it, the fact that it is a manifold, or you could pick up on the two connected components part of it, the fact that there are actually two clusters. These are not our Gaussian shaped clusters, of course. So, we still have to do something nonlinear and geometric, but there are in fact two clusters. So, I want to give you something where this confusion does not arise, and so I am going to say I am going to give you two positive examples, two negative examples, and now I am going to ask you, what is the label of this? It is very unclear from the data set that you have what this label should be. Now, I am going to give you infinite amounts of unlabeled data, and I am going to ask you what is the label of the black point. And I think you see, again, if you are a reasonable person, and it is late in the day and you would probably like to be reasonable at this time, it is going to be red. So, geometry is important, and the situation we have to deal with is that we do not know the unlabeled data, but we have a bunch of points. So, we are going to use the unlabeled data to estimate the geometry and use the geometry to penalize correctly, and this is what we called manifold regularization or geometric regularization. Okay. So, this gives us something like this. You do exactly what you did before, but you throw in another penalization, and so given a function f, you want to penalize it intrinsically according to some norm f of I, which is defined intrinsically on the manifold. Now, there are a number of candidates for f squared I, okay, and that's a whole, every game that you've played over the last 50 years in Euclidean space can be played here. So, the most natural choice is the Laplacian and all the variations of the Laplacian, the iterated Laplacian, the heat kernel, and other differential operators. Okay. Now, this doesn't give us an algorithm yet, because of course, you can't compute that guy, because to compute that you still need to know the manifold, right. So, this brings us to the heart of the matter, which always comes up whenever you do anything like this. You are given a manifold, you are given a bunch of points. In this case, these were the unlabeled data sets. How do I estimate something on the manifold? In this case, some intrinsic norm on the manifold, or the Laplace operator on the manifold. Okay, so M is unknown, but what you have are a bunch of points sampled from M. This is what you would have liked to compute, okay, if you had known this manifold. But what you do instead is that you make a graph, which roughly speaking connects nearby points to each other, but for technical reasons actually it's better to use a complete graph. Okay. But the picture I want you to think of is this local neighboring graph, and then this graph has a Laplacian defined on it, the graph Laplacian, and because of her identity that can be written like this. And see, you wanted to make the function f smooth on the manifold. Here you are trying to make the function smooth on the graph, so that from point I to point j the function does not change very much if I is connected to j. If I is not connected to j, then you do not care. So, you see, this is an approximation to this. So far it is just a heuristic approximation. So, on the left side of the picture is the continuous world. There is the manifold, there is the Laplace operator on it, there is this quadratic form. This is essentially Stokes' theorem that this is equal to this. On the right side, you have the discrete world, where you have the graph, the vertex set, the edge set, functions defined from on the vertices of the graph Laplacian defined that way, this quadratic form, and this is equal to this, and that is a few lines of linear algebra. Okay. So, then what you have at the end of the day is this algorithm, and this is an algorithm. Okay. I give you some unlabeled points, I give you some labeled points, you choose a kernel k, and now you do this. You may think of this as actually a method by which you start with a kernel k and then learn some new kernel k prime. So, you can actually write this whole thing as just doing standard regularization with some new kernel k prime, which can be written in this way. Okay. And so, for every classical algorithm which can be accommodated in this framework is one where you just have to set gamma I to 0. The moment you set gamma I to 0, you get a classical algorithm. And for every classical algorithm, if you do this, you will get the Laplacian version of that classical algorithm. So, you will get Laplacian support vector machines, Laplacian logistic regression, Laplacian this and Laplacian that. So, I will show you the example for Laplacian support vector machines versus ordinary support vector machines. Okay. So, here is just an example. There is a positive red and a negative blue and a bunch of unlabeled data, and this is the standard support vector machine, the inductive support vector machine, not the transductive SVM. Okay. So, what does the inductive SVM do? It looks at the red, it looks at the blue, and it just has to build a classifier. Okay. So, you are always working, by the way, here with the underlying Gaussian kernel. Okay. So, the support vector machine is working with a Gaussian kernel, so it has the ability to make a nonlinear classifier. But of course, in this case it will actually just build a linear classifier, because it will put a Gaussian on one point, a Gaussian on the other, and the sum of the two will give you this linear hyperplane, the max margin hyperplane. Now, this is the case where gamma I is equal to 0, and as I keep changing gamma I from 0, you see the solution starts curving around. And that's how Laplacian SVM differs from standard SVM. Of course, when we curve around, we feel that this is a more satisfying solution. But we have really no basis to feel that. This is just our prior belief that somehow this is more satisfying. Okay? And indeed, if nature were malicious, it could be that this was the right classifier to have built in the first place. Nevertheless, in lots and lots of experiments that we have done over the years, we've actually found that this method always gives you improvements. Sometimes the improvements are modest, and sometimes the improvements are quite startling. So, in this example, coil 20, the error rate dropped from the standard SVM, which gives you an error rate of 24.64%, to 3.66% using a Laplacian version of this SVM. And in some others, the improvement is not so much. Okay. So, what we see this watch is working, right? It's not, because it seems to be stuck at okay. Okay, what we see is that using this Laplacian to penalize functions actually allows us to build a very good classifier, and we can use unlabeled data to do very well. So, now let us actually try to build some theory. If none of these actually worked in practice, then there was no point proving theorems. Okay? So, there are lots and lots of experiments we did over many years and several graduate students, and it just systematically always was working. So, now we need to understand what is going on, something is going on. So, here is a gap between the optimal classifier, the Bayes risk, and the classifier that we built using gamma A and gamma I and n, where n with n unlabeled points.
Just off the previous picture where you have the green. Well, no, that one, yeah. So what you're doing is you build the Laplacian and then let the Gaussian diffuse somehow under the influence of the Laplacian. Is that what you?
Right. So, you are working in a space of functions, and you are actually just doing this algorithm. See this algorithm? You pick a space of functions f, okay, which is defined on R2, and now this you do least squares, say. You take the norm of this function in R2 in this reproducing kernel Hilbert space, as they call it, and then you make a graph connecting nearby points to each other, and you apply this. And actually, for reasons that are well understood, this actually gives you a polynomial time algorithm. So, you get the global minimum of this by solving essentially a linear system. So, okay, this is the gap, and what I want to show is that this gap depends on C and the norm of the regression function in two different senses. Okay? So, there is the norm of the regression function in the original reproducing kernel Hilbert space in which you are operating, and the norm of the regression function just on the manifold, which is the second part. Okay? Now, if you look at all these constants, this constant u squared, which is related to the eigenvalues and eigenfunctions of the Laplacian on the manifold, is an entirely intrinsic object. This object, kappa squared, is the supremum over x of k xx, which to anyone who's done analysis with these kernel methods is a very familiar object. Okay? Now, what are the classes of problems on which this method is going to work? It's actually precisely those problems where the external norm is actually very high, but the intrinsic norm is actually very low, because then you can set gamma A close to 0 and gamma I to be non-zero, and get a rate which depends on the intrinsic norm being very low. So, if you did not use the intrinsic norm and you just use the extrinsic norm, you would get this poor rate, but if you use the intrinsic norm, you will get a different rate. I will come back to this because these are only upper bounds. Okay.
What is your manifold here? Because you use the discretization to define your procedure, but here you have the manifold in the result. So
very good, very good. Yeah. So this is a incomplete theorem. Incomplete in our, I mean, it's a correct theorem, but it doesn't give us the true picture, because this theorem assumes you actually know the manifold.
and the data
So
are
it's an oracle
from the
theorem.
manifold uniformly or something, or how is the data related to the manifold?
Okay, so that's let's assume it to be uniform for the moment. Okay, I'll come back to that question. It's an important one, but let's assume right now it's uniform. Okay, yeah. So it's a random design uniform regression. Now, as you say, this theorem is actually telling you what would happen if you knew the manifold and used a different kernel, a kernel which was adapted to the manifold, rather than a kernel which is an extrinsic kernel. So, I want to actually give you the following invocation. There is only one kernel, there is no kernel but the heat kernel, and the only thing that changes is the domain. So, if you are living in a high dimensional space and you think this is the space, you will use the heat kernel for that space. What is the heat kernel in Rn? It's just the Gaussian, which is what everyone uses, the Gaussian kernel in all these methods. But if you suspect that your domain is some manifold M, then you should actually use the heat kernel for that manifold as the kernel to do all your estimations. So, this algorithm is essentially trying to approximate the heat kernel by throwing in that Laplacian term, okay? And this is essentially the rate you would get if you use the heat kernel and knew it. But now comes the question, of course, you don't know the heat kernel because you don't know the manifold. So, now we have to understand, can you learn the Laplacian or the heat kernel on the manifold, and in fact, is it the case that as more and more data come along, unlabeled data comes along, your graph Laplacian converges to the manifold Laplacian?
Before you go to that, can you go back to the last slide?
Right.
Something basic I'm still missing. Suppose, as you said, I mean, because I don't remember what EOP is and so forth.
Yeah.
So I don't know what your definition for the moment of FOP is. Is it the
F-opt is the regression function,
true regression
the
function?
true regression.
Okay, so where in this inequality do I see the case that if the marginal distribution of x, that is the manifold, has nothing to do with the law of y given x, you were wrong, our intuition was wrong in all those examples you gave us, and knowing things lived on a circle, the truth, which you should have still used the straight line, where do you suffer in this?
Yeah,
formula?
that would be cases where this is large, F-opt is large, because the regression function is not smooth with respect to the manifold. So, its derivatives along the manifold are huge.
Okay.
It could be non-differential with respect to the manifold, could be infinite. So, case 1 is where this is large and this is small. In this case, you are going to be fooled by trying to learn the manifold and do all this, making it smooth with respect to the manifold. Case 2 is when this is small and this is large, okay? And that's the case where the manifold is helping you. Now, I'm going to make a claim about nature, okay? And that if data actually lives on a manifold or close to it in a high dimensional space, okay, then the regression function will be smooth with respect to the geometry of the data. That's just a claim about nature I'm making, okay? I have no basis except the experiments we've done, okay? So, it's somehow an argument in two parts. The first part of the argument says in high dimensional spaces data cannot be uniform. It has to concentrate along some geometric structures. That's part 1. Part 2 of the argument says not only does the data concentrate along geometric structures, the regression function is precisely smooth with respect to those geometric structures. Which means, in another way to say it is, the regression function has a compact representation in terms of the eigenfunctions of the Laplacian. Okay. So, this is the basic key point. Okay? The graph and the manifold Laplacian, what is the relationship? So, as the data, as more and more data comes along, are you going to actually estimate the graph Laplacian, the manifold Laplacian? So, there has been a lot of results along this line by a number of people, okay, which essentially says that if you consider a fixed function f, okay, and then you look at the graph Laplacian and you evaluate the graph Laplacian on that function, as more and more data comes along, you will actually converge to the value of the manifold Laplacian. Okay. Now, I should say one thing which is not so by the way, this rate turns out to be depend only upon the dimension of the manifold, but you know, this is actually a pointwise statement. It is saying that an empirical operator, the graph Laplacian, applied to a fixed function f will converge to the true operator applied to that function. Okay. So, it is important to clarify this, because the reason I want to say this is it actually took us 5 years to prove something which I just want to make sure you understand. So, here is the empirical operator, the graph Laplacian, apply it to a function f and evaluate it at a point x. You get a number, it is a random number. This converges to Laplace m applied to the same function f at that same point x. Okay? This does not say anything about spectral convergence. Whether the eigenfunctions of this graph Laplacian converge to the eigenfunctions of the manifold Laplacian is not implied by this at all. Okay? This is a very weak kind of convergence. So,
if the data are not sampled uniformly from the manifold, then
right. Let me come to that question, because I think the next slide is precisely about that. Okay, so when you have data which is not uniform, there is actually something called the weighted Laplacian. So, here you have a manifold M which is subset of R k. Okay, so, here is your manifold in R k. It gets its Riemannian structure from R k. Okay, so, it is a submanifold of R k. Now, this has a Laplace operator defined on the manifold, but now you can consider a combination like this, a pair which is a manifold M just as before, along with a probability measure on this manifold, a probability distribution function on this manifold, and this gives this is called a weighted manifold, and this has a Laplace operator called the weighted Laplacian, which is actually roughly speaking delta plus grad p grad f. So, it is the ordinary Laplacian plus a drift term. Okay. This leads to essentially the Fokker-Planck equation. Okay. So, what the theorem, this theorem says, if I have a manifold, sample it uniformly at random, look at the empirical graph Laplacian, apply it to a fixed function, it will converge to delta m. Okay. That is what we proved first. What Lafon and Kaufman did is to show that if you look at the weighted Laplacian for an arbitrary probability distribution, this is still true. This will converge now not to delta m, but to delta p. That is what Lafon and Kaufman proved. So, that is the answer to your question about arbitrary probability distribution. However, neither of us were able to show until very recently that the eigenvectors of the graph Laplacian converge to the eigenfunctions of the Laplace-Beltrami, and as you know, all of us who use this use the eigenfunctions and the spectral decomposition heavily. Okay. There is also this issue of noise in another setting, in another sense, which is What if you have noise in the normal, so it doesn't lie exactly on the manifold, but there is noise in the normal directions? Then what happens? So then it turns out there are some kinds of noise that can be handled and some kinds of noise that are a little trickier, and I won't get into that discussion immediately. Okay? So it turns out this kind of coin tossing noise is very easy to handle. This is a little trickier, but I'll come back to the noise issue later. So there are many questions: how to handle noise theoretically, practically, how to choose the graph neighborhood, how often do manifolds arise in natural data, can you identify problems, and so on. And I should say, one of the things that interests me quite a bit philosophically is this business of manifolds assumes data lives on a manifold, and people give you widely different reactions when you tell them that. Some people think it's the most natural assumption you can imagine, and some people think, oh, data cannot possibly live on a manifold. It's the kind of thing some mathematician would make up, and yet they believe in linear functions. Okay? So in some sense, I want to say that I want to make 2 points. First of all, remember that Rn is a manifold too. So everything that I've told you on a submanifold is of course true in Rn, and so you could go to the weighted Laplacian in Rn if you're using spectral methods. The second point I want to make is, if you look at a manifold and noise in the normal direction, that is actually quite general, because that is like your mixture of Gaussians. You take k points, and those are like your manifolds with k connected components, 0 dimensional, and then you put noise in the normal direction. So we'll see that. So once you take this point of view, there are lots of connections to many different areas. Okay? So clustering, homology, volume estimation, solving PDEs, random matrices, all of these somehow are linked, and I'll give you just a sense of some of these directions that we have been pursuing over the last many years. So if you want to solve a PDE on the manifold of the Laplace type, what you would normally do is you would have to triangulate the manifold, use the finite element method, and then use convergence arguments. This may lead to the possibility that you could make a random mesh, solve it on this random mesh, and get an answer. Okay? Now, as I said, there's a random matrix argument at the heart of it, which is the random graph Laplacian converges spectrally to the true manifold, and I'll tell you about that. But I'll talk about homology and volume estimation. So let me first tell you about the random graph. Okay? So here is the basic key result that we were able to show very recently, and that is this: consider a compact submanifold of Rn, sample it uniformly to get a bunch of points. Okay? Now consider the matrix W, which looks like that. Okay? Where D is the dimension of the manifold. So that's the matrix W. Okay? That's a random matrix. Okay? And then the eigenvalues and eigenvectors of this random matrix converge to the eigenvalues and eigenvectors of the true Laplacian, provided t goes to 0 in a certain sense. Now this should be compared in some sense to a result which is very classical and very nice due to Patodi and Dodziuk and so on triangulated manifolds, where there's a certain way in which you can subdivide simplices, then the Laplace-Beltrami operator, and actually I think Patodi showed it for forms and everything, converges, and that's the basis of the finite element method. And so this is somehow the basis of the random solution of PDEs. No, t has to go to 0. T has to go to 0. Okay.
I mean P, not T.
Oh yeah, D is fixed. Yeah.
T is fixed.
Yeah,
It's
D is
not lost.
D is the dimension of the manifold, and it is what it is. Yeah. Yeah. So now there is a kind of a minimax argument to show that actually understand what are the problems on which the manifold, knowing the manifold can actually help you. Okay? And maybe I won't go over that in interests of time, but essentially the argument is this, that suppose your regression function, just suppose your regression function can be expressed as a linear combination of the first 3 eigenfunctions of the Laplacian. Okay? Then if you don't know the manifold, you don't know this basis, and therefore you have to use some generic method to learn this regression function, and you will get a rate which is non-parametric in the dimension of the manifold. Okay? However, if you know the manifold, you know the basis, and you'll get a parametric rate, because you know the basis, you know the regression function can be expressed as the first 3 linear combinations of this of the eigenfunctions, and so you'll get a rate that is parametric versus a rate that is non-parametric. So if you say that the function is smooth with respect to the manifold, that says that essentially the function has a compact representation in terms of the eigenfunctions of the Laplacian. And there are 2 different ways in which one could write it. Essentially, a Sobolev space on the manifold is simply f can be written as alpha I phi I, where summation alpha I squared lambda I to the s is less than infinity. So functions of this form, which can be, these are intrinsically written in terms of the eigenfunctions and have a decay in alpha, these functions can actually only be learnt by a manifold based method, and there is a separation you can show between any algorithm that doesn't know the manifold and an algorithm that knows the manifold. Okay? But I won't tell you. So actually that's a class of problems on which knowing the manifold can help you, provably, and then the question is, how do you know the manifold? You can know the manifold by collecting a bunch of unlabeled data and then trying to learn it. So now I'll talk about 2 things in about 10 minutes. The first of these is homology. Okay? So you see, from many points of view, it becomes very important for us to learn the manifold, because if you know the manifold, there are lots of things you can do. So we started looking then at this very abstract question of, I know a manifold, what can I learn about this manifold from points? So the simplest question you can ask is, can you tell me the dimension of this manifold? Okay? So it turns out that you can ask more qualitative questions, like suppose you know there's the 2 sphere and the 2 torus, and you want to know, well, the dimension is 2, but is it the sphere or the torus? So you have questions of this sort. Can you tell me how many connected components there are? And there's a whole tradition of a group of people in what is called computational geometry who work actually on computing homologies and things like this, and some of them also work in dynamics. And I'm going to skip through many, and I'm going to tell you an algorithm for computing the homology. So here is a manifold. I give you a bunch of points, which are a cloud of points sitting on this manifold, and now what I can construct is this empirical set U, which is the union of balls of radius epsilon centered at the points. So I've got this union of balls epsilon, radius. So what you can prove is that if epsilon is well chosen, then the homology of U, which you can construct because you know it, this is an object you have, is equal to the homology of M, and this is actually captured in the following kind of a theorem. So if M is in RD, then if you draw at least so many examples, then there is an algorithm that will recover the homology of M exactly with probability greater than 1 minus delta. Now if you look at the sample complexity, you see M is a k-dimensional manifold embedded in a d-dimensional space. The number of data points you need depends only on k. It does not depend on d. So it's completely independent of the ambient dimension, depends only on the intrinsic dimension, and that's the rate. Now what is the actual complexity of this algorithm? Because to read a d-dimensional point takes you d steps, of course, right? To read every data point itself is going to take you d points, but you have n points, n is independent of d, but n points can obviously live in an n dimensional subspace of Rd. So, what you have to do is read every point, that will take you n times d steps, project into Rn, and then work entirely in Rn. So, now it is linear in d, the computational complexity, and the informational complexity is independent of d. Okay. Turns out that what is the algorithm? The algorithm is actually making a simplicial complex rather than a graph. So, the graph is I take 2 points and connect them if they are within epsilon of each other, which is the same thing as saying the balls of radius epsilon by 2 intersect. So, connect 2 points if their epsilon balls intersect. Now, I can make a j face by connecting j plus 1 points whose epsilon balls intersect, and that gives me a canonical simplex. This canonical simplex has actually a combinatorial Laplacian, which of which people in statistics and computer science have probably usually only looked at the first of these Laplacians, which is the graph Laplacian. The graph itself has 2 Laplacians really, the vertex Laplacian and the edge Laplacian, and the simplicial complex has many Laplacians, and it turns out that this situation is actually robust to noise. So, this actually leads to the following thing, you can ask, okay, if the data is supported on a manifold of dimension k, all my rates depend only on k. What happens if there is a little bit of noise in the normal direction? Suddenly the support of the probability distribution has gone from k to d. Do you immediately lose your rates? That shouldn't happen, because it would be terrible if that did. So, it turns out it does not in this case, but all of these are not completely well understood by me at least, because in some cases we know we can prove that it does not, in some cases we suspect that it does not, but we can't prove it. The last thing I want to tell you about is pure computer science, but it interacts in a very interesting way with statistics. Okay, so we have seen one example of regression more or less, where unlabeled data helps you and the Laplacian appears. We have seen another example of homology, and the simplest homology question is how many connected components are there. Okay, that is like clustering. That is a question a lot of people are interested in. So, what the homology question is actually asking the more general form of that question, and there again the Laplacian appears. And now, here is a third case in which the Laplacian appears very surprisingly to us. This is volume computation. So, this is something which people have thought about for a long time. If I give you a convex body in Rd, is there an algorithm that can compute the volume of this convex body? It turns out that it is known that there is no deterministic algorithm that can compute the volume of a convex body in polynomial time. Okay? But then in a breakthrough in 1991, it was proved that there is actually a randomized algorithm due to Dyer, Fries and Kannan, which actually computes the volume of the convex body in polynomial time. Okay? Now, then the next question is, can you compute the surface volume of this convex body? Okay, and Lovaas posed this as an open question in 1987. And between 1987 and now, there is essentially only one paper which shows that actually it can be computed in randomized polynomial time, but it's d to the 9. Okay. Now, I will just give you the idea of an algorithm that actually cuts this down from d to the 9 to the d to the 4.5, showing therefore that computing the surface volume and computing the volume are basically equal. And this is the idea. Okay. So, here is my convex body. I want to actually compute its volume, its surface volume, and what I do is I start with a distribution of heat. I imagine a distribution of heat inside this convex body. So, uniform distribution of heat. I can simulate this distribution because it is known how to build an efficient sampler, uniform sampler of the convex body. Okay. Now I'll run the heat equation, and I'll let the heat diffuse out of the body and measure how much heat is diffusing out of the body. And the amount of heat that diffuses out of the body is going to be controlled by the surface volume of the body. So if you use this idea, and of course the heat equation is the thing that relates the Laplacian to the heat kernel, turns out you can actually get something which shows that you can compute it in d to the 4, and this gives you a class of diffusion based methods that can sample manifolds and can actually compute the volumes of these manifolds. And if you can do this efficiently, then you would be able to solve PDEs on manifolds, you would be able to solve integration problems on manifolds, and you would be able to do a lot of things by randomized methods where deterministic methods become intractable, because triangulating a manifold in high dimensional space is also hell. So I've just given you 3 examples where there are clear theoretical results which point to how you can avoid the curse of dimensionality by taking this very geometric point of view. One is the computational curse of dimensionality. How can you make a procedure to construct the volume of a convex body that scales polynomially in the dimension of the body? Okay. And sometimes we've seen the informational complexity where the sample complexity depends upon the dimension of the manifold. And there are a number of very nice questions actually at the interface. Somehow all of them have this algorithmic flavor. There is some geometric object. I would like to approximate some property of this geometric object and construct an algorithm, and I would like to make this algorithm by actually sampling this object and then inferring the property. So this is some kind of so there are connections therefore to all these areas, algorithms, graphics, PDEs, machine learning, and so on. And I hope I've been able to give you some sense of how taking this geometric point of view has been very productive in trying to design new algorithms with properties that we cannot replicate by any other method, at least at the moment, in a variety of settings. So I'll stop here.
Any comments?
So are these methods really confined to manifolds? I mean, for example, if you have just a cross, plus sign, embedded non-linearly in a high-dimensional space, couldn't you find out something about that?
Yeah. So actually, yeah, right. So good. So it depends on what you want to find. So if you are looking at the at homological questions, then actually there are results due to some people who have shown how to do this for more general spaces than submanifolds. So certainly the cross can be handled. Now, if you're looking at questions of the Laplacian, then you have to figure out how to define the Laplacian appropriately for these spaces. So locally, of course, often they are just actually have a manifold structure. It's just globally they may not at every point. So if you're interested in pointwise estimates of the Laplacian at points where they are essentially locally embedded, then you can. However, you can do the heat equation in a certain sense more generally than the Laplacian if it's a non-differentiable object, because you may consider a metric space and then look at the heat equation on the metric space. So if you look at the cross as a metric space, which is almost like a manifold almost everywhere essentially. Yeah. So some of those questions can be handled, some of those cannot. And it really depends upon which particular question you're interested in. So for example, we know that the Laplace-Beltrami can be on functions can be estimated from on a manifold from essentially the graph spectrally as well. But we don't know anything about the higher Laplace-Beltrami on forms. Now, it's very natural to think that if you look at the simplicial complex, look at the combinatorial Laplacian of the simplicial complex, and you look at a weighted version of this where you weight it by the volume of the simplices, which is exactly what we were doing for the graph, weighting it by the volume of the edges, that should converge to the Laplace-Beltramian forms. Yet this is open as far as, I mean, I don't know if that is true. Even for manifolds. You know, for example, that from Nash's theorem that a Ka manifold can be embedded, roughly speaking, isometrically in R2k plus 1, yet we don't know how to construct an algorithm that would do that.
I think it's more than 2k.
Yeah,
3k or 2.
it's 3, yeah. So there is, there's the matter of which how many, the differentiability of the isometry, I think. Yeah. So we actually cannot get any of those embedding theorems, except maybe some very weak form of Whitney's theorem, which is not isometric, because that you can more or less achieve by random projections.
Next question. If your data is not uniformly sampled on a manifold, and is that possible you put too much weight at the point, you have too many points? You know, suppose around 1 point, you know, the density is really big, then you know, is there, you know, from your algorithm, you may put a lot of weight there.
So the question is, you have a manifold, you have some probability distribution on this
Right,
manifold,
on a manifold.
which you're sampling from.
Right.
And now I think if the probability distribution is low, density function is lower bounded by something,
Then it's all right.
then it's okay. But if it's not, then yeah, then of course you won't recover anything actually from it. None of those theorems would work. So the density has to have some regularity conditions.
How much dependent is the method on the choice of the graph?
On the
How much choice of the graph? So you are choosing a graph in certain way. So if I choose a different graph,
well, it's not very, it depends really on the scaling. So actually what we want to say is you make a complete graph and you look at edge weights which look like this. Essentially e to the power of minus xi minus xj squared over t, actually 1 over t to the power of d over 2 plus 1, and t itself is a function of n, and tn is equal to 1 over let's see, n to the d plus 2 should be going to infinity, something like this. That's roughly, but anything which has this general property, it doesn't have to be actually a Gaussian, but any kernel which has the same decay property would work. So when I say graph, it's really a complete graph. The graph is uninteresting. This is a complete graph with all points connected to each other but weights. Now you can also approximate it by the ball. So that would actually be a sparse graph. Curiously, I think we failed to prove that with the ball you get spectral convergence, but pointwise convergence is true. But I don't know if spectral convergence is also true. It may be.
What about, you need, D is the dimension of the manifold there, or the intrinsic?
Yeah, that's the dimension of the manifold.
And so in practice, I know that's just theoretical for some
Right.
theorem, but in practice, since you don't know the dimension of the manifold,
Right.
what are you choosing?
Usually, we've always chosen this via some kind of cross-validation procedure based on what problem it is that we are actually trying to solve. So most of the experiments that we have done have been in this semi-supervised setting. So I have a bunch of unlabeled data, I have a few labeled data, and then I want to make find a regression function. So then I choose a graph with some parameter t, okay, and then do cross validation to find the t. That's what we've done in practice.
to the mark. Otherwise, let's thank all the speakers of the